Okay, this talk is about measuring delay and reporting delay in routers. Obviously, packet delay is an important metric. It's important for real-time applications. And if you're in charge of a network and there may be SLAs relating to delay from one end to the other, then that's important for you as well. Obviously, building block of end-to-end delay is delay in an individual router, and that's what I'm talking about here. Now, if we wanted to try and measure this using active probing, we'd be in trouble because it's very difficult to get an accurate idea of what's happening inside the network with active probing. Passive would be extremely expensive. You would have to have infrastructure on input and output interfaces. So really, this is a case where we'd like to have the router itself report delay statistics. The problem is, at the moment, there's essentially nothing reported, nothing measured, and nothing reported about this. So the aim of this work is to take that situation where we have essentially nothing and to be able to report not just some average delay, but in fact quite rich information about delay. The problems are basically, how can we first of all measure delays inside the router, what statistics should we take from them, and then how can we report them back? The background to this work is we have a fully instrumented router with a GPS synchronized hardware measurement on all input and output interfaces. So it's a very complete set of data, billions of packets, terabytes of data, and we get to monitor almost 100% of that. I'm going to focus on an access link. The access link being controlled by a customer, they have the right to drive things up to high utilization levels than might otherwise be the case, so we can see more interesting delays there. Here we have this OC3 link on the right-hand side. That's the output link, and it has 4 inputs. The main ones are 2 OC48 links, which carry about 50% of the traffic each. And we see we can match the packets, again, almost 100% packet matching. So we really have an accurate handle on what's happening here. We need to be able to understand how the delay is, builds up as a packet traverses the router. First of all, there's the store portion of the store and forward router. Actually, let's not worry about that. We already understand it, so we don't need to model it. Next step is the packet goes through the front end of the switch and across the fabric. We're going to model that in a simple way as simply a packet size dependent constant. And then the output queuing, that's the queuing and the serialization in the output buffer, we model that as a FIFO queue. So we have this very simple model. Front end is just a simple delay, and the rear end is just a FIFO queue. Very simple, but let's see how it performs. The black dots are measured delay values, and this is what the model says. So it doesn't look bad. Looking over a much longer time scale, here we have a busy period. What we're looking at here is essentially the router delay build up as a function of time. It goes up and up as the router builds up, as the output queue builds up, and then drains off afterwards. We're seeing about 5 milliseconds there. The measured and the model are overlaid there. We can see that they're virtually directly on top of each other, so the model's working very well. The difference is in red. It's in the microsecond range, apart from a few spikes. So we can get a handle on delays through the model. What should we measure about them? Well, the key is busy periods. A busy period is simply if there's a packet going through the system's busy, and if there isn't, the system's idle. By focusing on busy periods, we get a key advantage because in this study we were able to timestamp packets and the beginning and the end of the router. But of course, normally we can't do that. But it turns out that in busy periods, if you're inside a busy period, you don't have to worry about that initial delta thing at the front of the router. You can just focus on the output queue. And measurements of output queues are possible in routers. For routers which implement active queuing management, you can access that, so we can measure this. The other reason is, of course, busy periods, basically all the action is happening inside the busy periods. Here's an example of one. Again, the grey curve is the busy period. It builds up from 0 as the buffer builds up and the output buffer reaches a peak, amplitude A, then goes down. We could measure those. Obviously, the durations and amplitudes of busy periods are one important thing to look at, and we could do that. We could, for each busy period, collect a single value, and we could come up with histograms of the amplitude that corresponds to the worst delay in a congestion episode, or histograms of durations of these congestion episodes, and we could discretize these and export them. But we'd like to do more than that. We'd like to care about busy period shape. So what is the shape? We see here literally the shape of that grey curve. That red curve is an alternative shape, a kind of an extreme case, which would correspond to all the packets arriving right at the beginning and then just draining off after that. Basically, almost any curve you can draw there in between the grey and the red, or in between the grey and the bottom, is a possible busy period for exactly the same duration and exactly the same number of packets, but a hugely different delay performance. For example, if we want to imagine if the delay reached a certain level L, and we were interested in knowing how, over what period of time did the congestion exceed that level L. What's the duration of that congestion period? Clearly, the shape of the busy period is going to determine that. Different shapes will give you different answers. If we model the shape of the busy period, a simple triangle, we can actually predict that. And now we can compare that simple prediction against the reality as a function of that congestion level L, and we see we can do fairly well. So we're getting two lessons from this. One, the shape of the busy period is really telling us important information about what's actually happening with delay, and B, we can really extract that information via a simple model. So how can we actually capture this shape? Well, a simple way we've just seen. We look at the amplitude and the duration of these busy periods jointly. Here we have a discretized 2D histogram. Basically, in the top right of this picture, we're looking at busy periods which are long in duration and also large in amplitude, like the picture you saw before. Whereas on the bottom right, we're looking at busy periods which are less likely, that's why it's in white, less likely, long ones which stay very low amplitude ones. Basically, this picture tells us what kinds of busy periods are likely and which ones are not likely. So how can we report this? The idea is everything is busy period based. At the beginning of the busy period, and we can measure that because we can just see when the queue starts to build up at the output interface, we timestamp the beginning of that. Inside the busy period, it's trivial to maintain the current maximum value that we've ever seen. At the end of the busy period, we timestamp that. We can then calculate the duration of the busy period. We've got the amplitude recorded, and we export those two values. In practice, for memory reasons, we'd have to export that into a histogram. We couldn't retain every single value. Now, at the end of some 5-minute window, we want to actually summarize all the information we've got and export it. How can we do that? First of all, let's look at the duration and amplitude individually. We create histograms based on equal population bins. By concentrating on equal population, we automatically focus on where the data is. We don't have to have some complicated algorithm to decide the bins or to preset them arbitrarily. We can actually define them where they should be. Those two n bins in 2D becomes n squared 2D bins. We can then calculate the densities in those bins and export them. Here's that picture back again. This was, in fact, I cheated, gave you the discretized version in advance. These bins are the different colored rectangles. They're not squares because the bins have been selected in both axes according to be equal population bins, as I said. So what we've got here is basically a discretized version where the complexity to choose the bin sizes is low and natural. Automatically focus on where the delays actually are, because they could be very widely varying in practice, and we won't know in advance whether we're talking microseconds or half a second, so we can't fix them in advance. And it's this extremely rich picture. We're not just going from nothing to giving, say, average delay. We're going from a picture which, as I showed you, is rich enough so that we can get basically everything we'd ever wanted to know about delay performance. So the conclusion is we have a model here for a through-router delay. These delays can be measured by the router. By focusing on busy periods, we can get this extremely rich vision of what's happening with delay. It's computationally light, and the memory is feasible. And then we can, basically with this 2D histogram, we can get answers on durations of busy periods, durations of congestion episodes, amplitudes of congestion episodes, and we can even, in post-processing, if we think of new metrics that are important that we didn't think of originally, we actually have a hope with the data we collected, as I showed you, to calculate or estimate what those metrics would be, because it's such a rich description. We have a publication accepted as Sigmetrics this year, available at that website, and related technical reports. Now, I've been told that we haven't got time for questions right now. Maybe. So perhaps I could take just one question maybe on that talk now before I go to my second talk. Come on, don't be shy.